So, okay, I have started the recording. So, yeah, why you were asking? So, this is a specific problem related to the machine learning also. What happens whenever we have so many features? So, in that features, suppose you want to predict the house or the price of a house, that will be in the form of any values, like it can be suppose $100, $200, or $300. So, what happens? This x is actually the data vector that will be applied to a matrix or any system that is represented by a matrix. So it will be feed to all the features, so that if it is feed to all the features, and whatever y you will get, and at the end of the features application, you would like to remove some of the features and you want to have some feature engineering or something like that, will be the work of data science. So that's why we want doesn't want to explode the input vector x, that will cause you gray this what is back propagation exploding if you go deep into the AIML. So that's why that's one of the constraint of the system. And also in wireless communication system also we want, so that it will not explode. And also at the same time we also want, whether if x1 x2 till xn you have vector, so you want x1 should be equals to x2, also you want x2 is equals to x3, so that it will not have so many complications and sorry, what is called flops. Okay, if it is equal, then definitely it will be having less number of flops as compared to some other values. So that's why we want the smoothness. D vector we will D matrix we will try to understand like what is that. Now, yeah. So if you see this, this is the primary objective, and if we this is one of the famous technical regularized inversion. You can remember this name. If what we are trying to do, minimize, we are also trying to minimize the norm of 2. Okay, why we are trying to minimize this norm of 2? Because this we want this x to be less. Okay, if we are minimizing this, to that's why it is less. Also, one of the thing is, sometimes we are minimizing two norms, sometimes we are minimizing one norm also. Okay, so that will also called regularized least square, and that will have the trade-off between uh, L1 norm and L2 norm. So it is a, as you can check in the as a homework, trade-off between L1 and L2 norm. So what is the formula of this? This is actually AX. So basically, this is the applied linear algebra course in AIML. So from your part, what you have to do, you have to check the application of these things where it is applied. So that was a good question, like why x is small. But yeah, you should also explore. This is 2 norm plus lambda. This is 1 norm. So here the sparsity or something was there. That is, curve was made based on this L. So you can check. So sparsity and check is there, so you can check these things in the as a homework. Okay, so yeah, moving ahead. So in this, why that lambda was not considered to be, so here we can see that b is not at all modified. So yeah, a tilde is equals to a this root over lambda I, and here if you solve these questions, so you will get this lambda I, and when lambda is equals to 0, so the same problem will come back, uh, minimizing the simple least squares. So yeah, this is a second example. Estimation of periodic time series if y belongs to r power t, where t is actually the number of data points or the time instance at which the time series is observed. So what happens? You have suppose that you are taking the measurement whenever you do the lab experiments. You take the measurements and you just observe like what is happening, how it is changing. Suppose you are measuring this throughput. Throughput is actually the total number of required data points per time. So you are having this T1, this you are having this T2 till Tn. Okay, so that is required. And now, if you want to estimate this time series data, that is x. So how can you estimate? That is one of the thing. And also, you want you want that this whatever observation you are taking at x at t1 and whatever observation you are taking at x t2, at least if not a very gradual change is observed between the two consecutive samples. So you are wanting this x1 is equals to x2, then x3 is equals to x4. Similarly, x5 xn minus 1 is equals to xn. Okay, so in that case, the D matrix will be created. How this dx will enable that? Because if you multiply with x1 then x2 to xn, so first column if you multiply minus x1 plus x2 is equals to 0, because this dx, okay, is equals to 0. So this is implying x1 is equals to x2. Okay, and that's why you are minimizing this thing. And this matrix plays a very good role, that 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 makes sure the smoothness of estimated x. Because if you change a very gradual, so it will be very different values, okay, peak values. But if you make sure the smoothness, then smoothness, so it will be almost same values between two tiny distances. Okay, so moving ahead. Actually, this week it is one of the most important week of all the overall the course, because in this week in this the eigenvalue, eigenvector, and the spectral decomposition, then this positive semi-definite matrices are talked about, and that will cause the that will form the basis of all the mathematics, AIML. So if you consider this A belongs to R n cross n and x 0 and such that Ax is equals to lambda x. So this particular thing lambda is called eigenvalue. So what is the physical meaning of this eigenvalue and eigenvector? So what happens? You have, suppose you have this matrices can be a function, and every function we are writing in the form of matrix. Okay, r power n to r, you are writing as a function. So if the function, suppose you are plotting this one, okay, this is a function, and you are having the direction. Suppose this so function you can write as a spherical also, any function you can write. But later what you're having a direction. Okay, so we are having a vector that multiplied to this particular function, and it will not change the direction of its orientation. It is not changing, but it is only having the scalar multiplication of that vector. Means the direction it is not changing. So you can consider a rotation. Okay, so why this vector is important? Because anyway the direction is not at all changing, so you can find the central moment. So it is important for central moment. So any function will have a central moment through which it is rotating, and it is not changing its direction. The only thing that is changing is the scaling, that it is can be scaled. The scaling factor that is given by is a eigenvalue, and the direction which causes this doesn't change, or the invariant, is called eigenvector, and it is defined for square matrices. Okay, uh, so it cannot be defined for tall and wide matrices. It can only be defined for square matrices. So this is called eigenvector, and this is called eigenvalue. Okay, so this also, it is also written this x is an eigenvector, is invariant and the reaction of A. So any action will be provided. Means if you are having action, means A x is equals to lambda x. So you are providing the action A into x, but it is not changing the direction, but is only changing by lambda. Sometimes lambda is equals to 1. Okay, so it is not at all changing the uh, magnitude as well, if the lambda is equals to 1. And in that case, the lambda is equals to 1 is an orthogonal matrix that we will take care later. Rotation matrix is one of the example of it. Okay, so how can you solve it? It's very simple. You just have to solve Ax is equal to lambda x. So for solving the linear, sorry, this lambda, you need to have this determinant equals to 0, and this is also called as characteristics equation. Why it is called characteristic equation? Can anyone tell me why it is called characteristic equation? Suppose this will have the function of, suppose A is a 2 cross 2 matrix. So it will have lambda 1, lambda 2. Okay. So it will be the function of lambda 1 square as opposed to lambda 1, lambda 2 plus 4. Okay. So if you replace lambda by A, the every matrix follows its own characteristic equation. Characteristics equation. So what it is mean? That's why it is characteristic equation. It is called characteristic equation because if you have lambda 1 square plus 2 lambda uh, plus 4 equals to 0. So if it is a characteristic equation of any matrix A, it implies that A squared plus 2A plus 4 is equals to 0. This mean that's why it is called characteristic equation. And yeah, please.
Shouldn't you write for I identity matrix there?
Yeah. Oh, that is it's okay. So it will be I only. So basically, what does this mean? And we know that for null space to be defined, this null space of A is actually what? Set of X such that AX is equals to 0. Okay. Similarly, null space of A minus lambda I is equals to set of X such that X should belongs to R power n, obviously, such that A minus lambda I into X is equals to 0. Okay. So that we know. Hmm? And then if you move ahead, this is also one of the most important thing. This matrix is not invertible. Why it is not invertible? Because anyway we are keeping this A minus lambda I as a determinant of 0. If the determinant of any matrix is 0, then definitely that matrix is not invertible. So if it is not invertible, there exists a non-trivial or non-zero X belongs to R power n such that this is 0. And since this is equals to 0, so X is not equal to 0. Okay, because this determinant is equal to 0. And this polynomial will give you the uh, eigenvalue. Okay, so there are some examples of eigenvalue calculation for some of the matrices, because when I was also doing, I used to get confused. So you try to keep your own pen and try to solve by yourself. Okay, so if you take one of this example and you find it, so what we found it here, uh, yeah, any doubt? Put up by your mic is on. Okay. Yeah. So in this way, we got two eigenvalues. Okay. Two eigenvalues, 1 and 3, and you got similarly, see, two vectors that doesn't change its direction. Okay. So these two vectors doesn't change its direction, and it can be scaled by 3 and 1. So that's what cert is meant to be here. And you also one more thing. So for one eigenvalue, you can have infinite eigenvectors, but vice versa is not true. So you can see one of the example here. If you have one eigenvalue, this T can belongs to many values in the R space. But the eigenvalue is one only, right? You have so many eigenvectors. For one eigenvalues can have so many eigenvectors because that vector is the whole R space. That's why you can have so many eigenvectors. Okay, so if you take this example of rotation matrix, so you have uh, complex eigenvalues. So yeah, one more thing. For complex eigenvalues, there are no eigenvectors. There are no eigenvectors. Remember, in R squared or R power n plane, but it do have in C n cross n plane. So that we are not this will out of the scope of this class, but yeah, if you want to read about this, you can read uh, from internet or something like that. But it also has some specific meaning. Why, what is eigenvector in C space? So that was very interesting. Okay, So if you see the reflection matrix, so we know that we derived this expression in the previous classes. The reflection matrix is Q is equals to I minus 2 UU transport, where U is the unit vector to V. Okay, that we are considering. Okay, this V is actually a vector. This is a unit vector. That's why if it is not unit vector, it will be divided by U square. Okay, so it is a unit vector. It is considered. So the basic principle that we started initially is QU is equals to QU is equals to minus U, and QV is equals to plus V. Okay, so what you can infer from it, V is also eigenvector corresponding to the eigenvalue of 1, and U is also eigenvector corresponding to the eigenvalue of minus 1. So this is actually eigenvector. These are two eigenvectors for reflection matrix. So this is also very important. That time we didn't talk about this eigenvalue and eigenvector. That's why we just ignored it. Okay. So similarly, if we have, and there are also some sort of matrices where we don't have enough eigenvectors. So here we can see you're having 2 0, okay, but you only have one eigenvector. So that is also not good for a spectral decomposition or the algorithm that we are going to apply in the future. Okay, this is one of the example of this matrix. So we talked about this. This is a summary. This Ax is equals to lambda x. X is the eigenvector. X is lambda belongs to R. The eigenvalues and the characteristics polynomial where this is given by characteristic polynomial is given determinant of A minus lambda I, where this polynomial the all square matrix satisfy its own characteristics polynomial. From that you can determine A square, A cube, or something like that. It will be helpful. Okay, so there are some properties that you need to remember. First of all, x belongs to R power n is actually the eigenvector of A corresponding to eigenvalue of lambda, provided this thing is there. And if you have, if you want to determine A power k, then you can have this eigenvalue of lambda power k that we can see here. Okay, A square is equal to lambda square. So directly the same influence is happening in lambda. Okay, so one property, and yeah, what happens sometimes we forget about these properties. So you try to check with the derivation as well. The derivation is simple. You are checking with respect to A square. Okay, and this x is eigenvalue of this the what is this I corresponding eigenvalue of x square is the I corresponding eigenvalue of A square. Okay. Similarly, k a lambda power k, a power k will have lambda power k eigenvalue. Okay. In particular, this if p is a polynomial in x, so if this is belongs to this x, x is the actually eigenvalue here. So we can write in the terms of a characteristics equation for a also, that we can make sure you can have a derivation for this. So this is very simple. Hmm. So if lambda x is actually the eigenpair of A, so for any real number, this A plus Si, so it will also modify the lambda will plus S. Okay, how it is very modifying? Because if you see A plus Si is equals to Ax plus Sx, so you can write this Ax as a lambda x and Sx as a Sx. So lambda plus Sx. So this is A, this is another B matrix is equals to this modified X. So the modified is the actual eigenvalue for B matrix. Okay, so this eigenvalue is also added by S. Similarly, the trace of a matrix is given by the sum of the diagonal entries of A that we can see from here. You can try having this. So if you write this A, B, C, D, so you can have determinant as 0. So you know that this A plus D is what? Sum of eigenvalues, the output of this eigen lambda 1, lambda 2. Similarly, this one is actually multiplication of lambda 1, lambda 2. So this is actually determinant, this is actually the trace. So what you have to remember, the determinant of any matrix is given by multiplication of the eigenvalues of that matrix. Similarly, the trace of any matrix is given by sum of the eigenvalues of that matrix. Fine. Similar matrices. So given the matrix A belongs to R power n, are n cross n. So if we have this, if P belongs to n cross n, be any invertible matrix, so Ax is equals to lambda x. Yeah, this is very important. Please don't. So what is happening here? We are trying to find a matrix, any matrix, and another matrix that is similar to A, provided you can write as, how you can write, A is equals to B A B inverse. Am I right here? Uh, no, no, no. This is wrong. Yeah. So what is happening here? I'm telling. Wait. B is similar to A, provided B A B inverse have
I,
same eigenvalue to A. Yeah. Tell me what was speaking. Who was speaking? Anyone? Yeah. So basically, this is the property, and you please remember this. We will use it in the spectral decomposition theorem. Okay. So if P is another
I
matrix.
excuse me. I
Yeah, yeah,
think
sure.
this definition. I mean, it should be B or some third matrix, invertible matrix P, such that P inverse AP equals to B. Then A and B are similar.
What you're saying again, please
Uh,
repeat.
A and B, two matrices are similar if there is an invertible matrix P such that P inverse AP equals to B. I
Yeah,
mean, B,
if you can write in the opposite way. I'm writing B is similar to A. You can write in similar way. A
if you
is, yeah. So again, this B is actually invertible matrix. That is for sure.
yes,
Mhm. You can write in this opposite way. A is similar to B such that there exists B inverse A. B
I mean,
has,
this is it necessarily B inverse? It is just an invertible matrix, not that particular B is needed. Any invertible matrix be there such that P inverse AP equals to B.
you are writing this B inverse AB is equals to,
No, I am talking about P. P for Partho.
okay.
P for planet. A third invertible matrix, any invertible matrix of compatible size, such that P inverse AP equals to B, then A and B are similar. I mean, this P is a basis change matrix.
Yeah, that is true. You are right. You are speaking
But if you
P is
use
equals to,
P, yeah,
P is
if
equals
you are
to,
P inverse A,
uh,
P
yeah.
is equal to B, B for Bombay now. Yeah, then A and B are similar. I mean, the same B should not be used for P. That will be very specific.
Yeah, yeah, yeah. That is there. Then you are telling A and B are similar. Okay.
Yes.
Okay, okay, okay.
Yes.
Any matrix can be used here, you are telling.
Yeah, any invertible matrix of compatible size.
Okay. So if B is similar to A, provided this, okay, any invertible matrix, fine. But here, sir used only B, right? This, this I agree with you. That is the basis
This is
chain
nothing.
matrix.
What is written there in Professor's note? There is nothing wrong in it. B inverse AB has the same eigenpair. That's okay.
But this P matrix will not have, this particular matrix will not have same eigenvalues as A.
No. Actually, this P is the basis change matrix. A and B are matrices similar in the sense they represent same linear transformation with respect to two different bases. And this P is basically the basis change matrix from alpha basis to beta basis like that.
Yeah, that will be there for basis change matrix. For that also, that similar thing has exists. But if you consider this particular thing, so forget about P. So this, if B is similar to A, then you can write, then you can say this statement means, the first statement means this particular thing. Similarly, the second statement means this particular thing have same eigenvalue.
I don't agree, madam. I don't agree. If
So
B is similar to A, you cannot claim that B inverse has to be equal to A.
no, I'm
It
not
is just
claiming
a,
equal. I'm telling same eigenvalue to A.
that means it is similar.
Yeah, that means it is similar. I'm not claiming that it's same. I'm not claiming anywhere equal. I'm
Okay.
telling because here you can see what as what it is. Ax is equals to lambda x. If you write ai x is equals to lambda x, and yeah, this that you're telling is used for changing the basis. I agree. Okay. If you write this a b inverse b is x lambda x, and if you reverse it and properly write it, so what it is showing, this particular matrix have the same eigenvalue, this lambda, which is eigenvalue of A, provided you also have
But a
the,
different eigenvector. Here it
yeah,
is important to note that the eigenvector is not remaining same
yeah,
with the similar
true, true.
matrix.
Similar matrices doesn't talk about eigenvector, but different vector is there. But it is only talk if any matrices can be written in terms of B, A, B inverse, and definitely it will have the same eigenvalue with respect to A. And the B matrix, that is a new matrix that curated, that is an invertible matrix that exists, it will be similar to A. That's what I'm telling.
Yeah.
So basically, let's try to understand this. B is similar to A. This implies B, A inverse B have same eigenvalue to A. First thing. Second is A is similar to B. This implies B inverse AB have same eigenvalue to A. This is the because the same thing will be used in spectral decomposition theorem that I'll tell. And this is there, yeah. This is there for basis chain vector, and P can be any matrix.
Yeah. Okay.
Yeah. Okay. So for any confusion, we will again come back to it. That's fine. But yeah, thanks for raising the point. Okay. So similarly, if the another perspective of this triangular matrix, the triangular matrix or have the eigenvalues as their diagonal elements. That's fine. So basically, the diagonalization of matrix. So here it is coming the diagonalization of matrix. So this is very important. Here it forms a spectral decomposition theorem. Hmm. So if A is such a matrix that has n linearly independent eigenvectors, you remember this is the eigenvectors. So suppose n cross n matrix is there, A, okay, belonging to R n cross n. So you have the eigenvalues if the columns of A are linearly independent, and you can have the eigenvalues as different eigenvalues, and also and if you have different eigenvalues, then you will have the corresponding eigenvectors, and if the set of that corresponding eigenvectors are linearly independent among each other. I hope all knows about linearly independent. So it forms as a set, and you are writing this set as x. This x is x1 vector, so on xn vector, where x1 x2 xn are eigenvectors of the corresponding eigenvalues of a matrix A. Okay, so you can write ax is equals to, you can simply multiply here ax1, ax2 till axn, and this this is lambda 1 x1, lambda 2 x2, so on lambda and xn. So if you write like this will go here, okay, because anyway this is a scalar multiplication, so you have to write like this. So this is x1, x2, 2 xn, and you're calling this matrix as x. Okay, so here this ax is equals to, and this matrix has x lambda. Okay, so this lambda matrix you can write like this. Here you can multiply by x inverse ax, okay, and or you can write a is equals to x inverse. So this is actually what we are talking about. Okay, so this is a diagonal matrix. So when you can say this A is similar to diagonal matrix, when you can say A is similar to diagonal matrix, when these X have linearly independent columns, because in that case X inverse will exist. So what I'm trying to tell, A is similar to uh, this diagonal matrix provided there is a linearly independent columns of X, and in that way X inverse will exist, because the eigenvalue will be same. A of eigenvalue will be same as lambda. So here we will see with some examples. So yeah, this is the actual thing, and how you can write, suppose this is A is equals to x lambda x inverse. Okay, so if you have this x as, suppose this is a symmetric matrix, so that we will take care later, but that's fine. So this is later, or we will see how this is actually the spectral decomposition theorem. So we are, after this we are coming to symmetric matrices. Okay, the symmetric matrices are always the eigenvalues of the symmetric matrices are always real. So what is symmetric matrix? First of all, it is A transpose equals to A. Okay, so this implies if we have AX is equals to lambda x, so what we are claiming that the eigenvalues of the symmetric matrices is always real. Okay, so if even the conjugate, so with we are proving it by checking by assuming whether there exists some non-symmetric non real number, non-real eigenvalues. So let's say it is lambda dash. So this ax is equals to lambda x can be written as a bar x bar is equals to lambda bar x bar. Here it is, because since a is real, so you can write like this one. So later, by multiplying a lambda to x transpose x, why I'm going through the derivation, because derivation is very important. How you go through. For example, you can have another way to prove that lambda is equals to this conjugate. In that way, there is always real existence of the eigenvalues for a symmetric matrix. So this is one of the way. How to think like this? This we can do. So we can do like this because we have to check. We have to involve this A transpose somewhere. So if you write like lambda x bar transport, so you can write like this. Okay, if you write like this, you can write like x transpose x conjugate transpose. So here the conjugate term will come. Once the conjugate term will come, so here you can write this um this conjugate. Okay, so this conjugate will come here, and in this way this is equals to this is okay, because anyway both are ax bar. So this is proving that lambda is real, or once the lambda is real, we know that eigenvector corresponding to the real eigenvalues is also real. This is eigenvector. Okay, so another thing is, first thing is, the eigenvalues of symmetric matrices, real matrices are always real. Now, the another thing is eigenvectors corresponding to distinct eigenvalues of a symmetric matrices are orthogonal. So suppose we are having two distinct, means lambda 1, lambda 2 are different values. So we have to prove whether there exists a orthogonal set. Okay, that's why we call this as a orthogonal set in the previous one. We have to find which the symmetric linear independence means if we prove that this X is actually the orthogonal matrix, then definitely the columns of X will be linearly independent. So in that way only we are going to the symmetric matrices. So if we have two lambda 1 lambda 2, as an eigenvalue of any matrix. So in order to prove that, we have to prove uh, this lambda 1, sorry, the corresponding eigenvalues is x1 transpose x2 is equals to 0. So inner product will be 0 for any two matrices, then it will be orthogonal. So if you write this x2 transpose a x1 is equals to x2 transpose lambda 1 x1 is equals to lambda 1 x2 transpose x1. So here this is normal A. Okay, now you have to incorporate somewhere A transpose. So if you incorporate A transpose here, so and again here you used x1, now you use x2. That's why then only we can compare with x1 x2. Okay, so this is the one way. So if you write this x2 transpose, here you can write ax2 whole transpose x1, and this 2 is equal because first you are considering this, then you are considering this. So if this 2 is equal, so this is giving you 0 because lambda 1 x2 transpose x1 is equals to lambda 2 x2 transpose x1. Okay, now lambda 1 minus lambda 2 x2 transpose x1 is equals to 0. Okay, so x lambda 1 minus lambda 2 can never be equal to 0 because we consider it this take eigenvalue. So x2 transpose x1 is equals to 0. This proved. Okay, now if we write A in terms of B inverse dB, so what we are saying, A is similar to D uh, if this B is having the orthogonal set. So, so how we can write this? This BA is equals to DB. So this is what it is. So A is equals to B inverse DB. So B is nothing but here. Yeah, yeah, please.
Yeah, actually, orthogonal vectors are okay, but to make the matrix, you have to orthonormalize them. Now, matrix will be,
Ortho normalize.
I mean, if
Okay.
each vector has to be normalized, only then it will be orthogonal matrix.
No, that will be orthonormal matrix. Like the name is orthonormal.
Orthogonal columns without orthonormal, it's a matrix. The columns needed to be orthonormal. Otherwise, this diagonalization will not happen.
Uh, okay. But that matrix name is orthonormal, where this is orthonormal and this is orthogonal. That is fine. That I agree. That
Orthogonal matrix has orthonormal columns.
orthonormal matrices have orthogonal columns as well as their unit, their norm should be equals to one that you're talking about.
Yes, yes, yes. Otherwise, when you put this B inverse and B, the product will not give you this B, A, B inverse will not be B. There will be a constant involved unless you orthonormalize them.
Okay, okay. Yeah, in this case, this auto normalization is required. But sometimes, whenever we talk about this orthogonals, doesn't every time means that the norm is equals to one. But here in this case, it will be required.
Yes, of course. I mean, as a vector, orthogonal vector is definitely different from orthonormal vector. But when you are making that matrix and you want the matrix to be orthogonal matrix, then the columns have to be orthonormal. Otherwise, it will not be orthogonal matrix. A transpose equal to I will not be satisfied unless the columns are orthonormal. Length of the column has to be 1. Otherwise, A
Yeah,
transpose will
A
come into it.
transpose equals to A transpose equals to I.
Yeah, it will not be I unless the columns are orthonormal. It will come to be some Ci. That is
Okay,
why
yeah.
individually vectors are okay. Orthogonal and orthonormal, it's different. Without normalization, you call them orthogonal. But when you make this particular similarity matrix B, which will diagonalize the situation for in symmetric matrix, it has to be orthonormal in columns.
Yeah, yeah, yeah. Okay, okay. Yes, yes. That I agree. Yeah. But generally, we ignore this term of orthogonal. Like by default, we assume that the it will be normalized. But
In
if this,
fact, okay.
huh,
That may be the case. I don't know because we mathematics people are always a bit more cautious. Maybe then it's okay. If it's conventionally meaning orthonormal, then it's okay. It has to be orthonormal. That's my point.
yeah, that's right. So in this case, this A is similar to D, provided this. B matrix that you're talking about should be invertible, means the columns of B will be orthonormal to each other. So if the eigenvectors of A are linearly independent, then a matrix A, okay, this matrix A is similar to the diagonal matrix D, whose diagonal matrices are essentially the eigenvalues of A. So this is very important. So what it is saying, this particular thing, if the eigenvalues of A are eigenvectors of A are linearly independent, means that we can write like this, then the matrix A from this expression is similar to D, okay, whose diagonal entries are essentially the eigenvalues of A. Okay, that we will use later. Okay, I hope this is clear. So this now if we talk about the symmetric matrix, the eigenvalues of symmetric matrix are always real. The eigenvectors of the are orthonormal. Okay, here orthonormal is used. Okay, so if for distinct eigenvalues, this is holding true. So if you just say with identity matrix, then this U1, 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 U2 to UN corresponding to the uh, eigenvalues of the identity matrix forms the orthonormal basis of Rn. So if because in that case, this is orthonormal eigenvectors of A corresponding to eigenvalues of lambda 1 to lambda n. Okay, so if you talk about this thing, you can write like you a similar way. Okay, and also why this is U inverse is equals to U transpose. Why? Because this U is actually orthonormal matrix or orthogonal matrix. Because the this is the diagonal matrix. Sorry, this U is actually this eigenvector matrix. And we saw that all the columns of the eigenvector matrix are like linearly independent, and they are forming they are also they are orthonormal to each other because they are corresponding to the unique eigenvalues of symmetric matrix. That's why they are orthonormal to each other, and when they are corresponding to unique eigenvalues. So in this case, this lambda 1 not equals to lambda 2 or not equals to lambda n. Okay, then only it will be uh, orthonormal. And in that case, this U transpose equals to U transpose U is equals to I. So you can write like U inverse is equals to U transpose. Yeah,
Yeah, all the eigenvalues need not be distinct. If some of them are repeating, the eigenvectors that you will get for symmetric matrix, in that case, those vectors can be, converted into corresponding orthonormal vectors by branch because
wait,
it can
wait,
be
wait,
proved.
wait. If we are talking about this or you're saying this
Symmetric
is
matrix, symmetric matrix, and these eigenvalues lambda 1 to lambda n, if they are distinct, it is fine. But if even if they are not distinct, still it
okay.
can be orthogonally diagonalized. In that case, the eigenvalues are regular in the sense that each one will produce necessary number of independent eigenvectors so that you can make this invertible matrix U. That means technically said that algebraic multiplicity of lambda will always be equal to corresponding geometric multiplicity because it is symmetric matrix. I mean, the point is all the
Okay,
eigenvalues
here
need not be
lambda, okay,
distinct.
I told that thing that lambda 1, lambda 2 cannot be equal. Okay, so
Yeah,
yeah,
some
this
of them
will,
may be equal. Some
right,
of them may be equal. Still, this is possible. There, you will have to apply Gram-Schmidt on those eigenvectors.
okay,
That's my point.
but here in that case, you'll not have orthonormal
You,
eigen
yeah, you,
this,
yeah,
huh?
you won't have automatically. You won't have them automatically. But then those particular, say, you have lambda coming twice. Then
Huh.
you will have two eigenvectors out of it. They may not be orthonormal automatically, but you can convert them into corresponding orthonormal vector
Okay,
by
okay,
Gram-Schmidt,
yeah.
and then it's for formation of this
Be
matrix
but anyway, we have to make sure that they are linearly
orthonormal.
independent.
Yeah, that they will be.
But in that case, this U inverse equals not equals to U transpose. That's what I
You
was.
will be. You will be because you will be made. The matrix U will be made only after orthonormalizing each of them.
Okay,
This
okay, okay, okay.
columns of U.
Okay.
That's my point. Suppose you are having a symmetric matrix where some eigenvalue is repeating itself twice or thrice.
Okay, that in that case we don't have to make it. It's
Then automatically you will get those x1, x2, x3 from one single lambda, but they may not be automatically orthogonal. You have to convert them into orthogonal and then into orthonormal vector and then put them in this u1, u2, u3.
yeah, that's true. That's what my meaning was also. If they are distinct, then automatically this will be orthonormal. Once this is orthonormal,
Automatically, yeah.
then
Automatically they will be orthogonal. Automatically they will only be orthogonal and then you have to normalize them and put in the matrix.
that is fine. That is fine.
Yeah. And
What
even
I'm
if they
telling,
are not distinct, even if
oh,
they are not distinct, still a symmetric matrix can always be orthogonally diagonalized by using Gram-Schmidt whenever necessary.
it can be always be diagonalized, but after doing only we can write this U inverse equals to U transpose. Otherwise, it
Yeah,
is only this U inverse. So this is the actual formula. But
yeah.
if you make this U as orthonormal matrix, then
Mhm.
only you can write U inverse equals to U transpose. So
Yeah,
this is a
and
base.
yes,
Yeah,
yes. And my point is, whenever you are starting with the matrix which is symmetric, this is always achievable. That you can make a U which is equal to U inverse equal to U transpose. That is achievable always, irrespective of the fact whether you have distinct eigenvalues or some eigenvalues repeating.
okay, I
Irrespective
agree
of
with your point that it is always achievable, but it is always not achieved at the initial point. Okay, so
yeah,
in that achieved, if it is not achieved in the initial point, you cannot write like that. If you have to make sure first that is U is a orthonormal matrix, then only you can write as U inverse equals to U transpose. So basically, you need to remember this particular formula, and if you find this U is U as an orthonormal matrix, then it will be converted to this one. And that is true that if it is a symmetric matrix, then it is always achievable through Gram-Schmidt. Okay. So yeah, so if you have symmetric matrices, then we are talking about symmetric transformation. So symmetric transformation can be written as this particular definition. Definition of symmetric transformation is this thing. If you have W belongs to R power n, be an n-dimensional subspace. The subspace can be any vector space. And if it is going from W to, so you know that subspace and vector space, I hope you remember during the funny initial classes, close under scalar multiplication and vector additions. All those will be called as subspaces. So if it will be a linear transformation and T is symmetric. So you are talking about the transformation and you're relating that symmetricity of the transformation with respect to symmetric matrix. So it should follow this particular thing. X transpose Ty is equals to T y transpose Tx. And if you represent any transformation by any symmetric matrices, so you can write like this: X transpose Ta y into y transpose Tax. This Ta is actually a symmetric matrices. Symmetric matrix. So what spectral decomposition theorem states? So it is actually abstract form. This if m less than equals to n and w belongs to R power n, meaning n dimensional subspace of R power n. So for symmetric linear function, that is a going from w to w. So here it was t. Okay, t. We have eigenvectors as this as orthonormal, and corresponding to each eigenvector, there is a real eigenvalue. So here if you m is equals to n is there, you can write a is equals to v d v transpose, because here this is I orthonormal is already given, so you can write like v transpose. So this is orthonormal, and this d is equals to uh, this particular matrix, because anyway any, so what is the eigenvalue theorem? This is also called eigenvalue theorem, a spectral decomposition theorem. Spectral decomposition theorem. So whenever we define any theorem, so how we define? First of all, for any square matrix, it can be written as A is equals to, this is V you can write, or X you can write. This is X inverse. Okay. If A is symmetric, then you can write A is equals to X transpose, where X is a set of eigenvectors, linearly independent eigenvectors, where this one is actually set of diagonal lambda n. So this is what spectral decomposition theorem or eigenvalue theorem states. But here, if you go uh, higher, then there is also uh, for anything you can write that the theorem which states, I forgot that name. Uh, what's that name? Okay, so here it is defined for square matrix. Okay, that theorem that I will tell, that will be defined for any theorem, that is UV we can write as I don't
That
remember.
should be singular value decomposition.
No, no, no.
SVD.
SVD, yeah, singular value decomposition. Nice. So singular value decomposition can be defined for any matrix. Okay, that not necessarily be square. So here that is a difference between this eigenvalue decomposition and but singular value decomposition that we will talk about. So okay, so this is just a proof that I'm not talking about this symmetric function. You can go through that because I need to go through the questions also. But the positive semi-definite matrix is very important that we will talk now. This whenever the theorem comes, you just remember the definition of the theorem and try to prove by yourself, because everyone way of proving is different. You can check later by seeing the sir proof, but first of all you should try by yourself. Okay. Now, what is positive semi-definite matrix? So first of all, positive semi-definite matrix is a symmetric matrix. Okay, a symmetric matrix, if that follows this particular condition, X transpose AX greater than 0, is called positive definite matrix. If it is semi-definite matrix, then X transpose AX is greater than or equal to 0. Okay, if equal to is there, then semi will come. Okay, otherwise no. But you always remember X for all X not equal to 0 in R power n. I hope this is clear. Let's see with some example. How will you define this matrix is like the positive definite or semi-definite matrices or not? You have to write X transpose AX. So if it is 2 cross 2, so X will be a 2 variable. Okay, so you can write like this, and you remember you can write like this, and you're finding this is always greater than 0 is irrespective of any value X belongs to R power n. So this is what say a positive definite matrices. Okay, so if A is symmetric, you can write always A is equals to U, this is gamma U transpose. As we saw for symmetric matrix, we can write like this. Okay, now we have some properties of positive semi-definite matrix that everyone needs to remember. Okay, so if you have lambda I ui be eigenpair of A, it means lambda is the eigenvalue, ui is the eigenvector. So you have to take ui transpose A ui greater than 0, and you can write like this. So what is the conclusion? Positive, why that's why the name positive came, because the eigenvalue is always greater than 0. Okay, positive name in PSD or PD, positive definite matrix, is there because lambda is always greater than 0. Suppose you have PSD, then lambda I will be greater than or equal to 0. Okay, first property. Okay, second property. So every eigenvalue of this semi-definite matrix is always positive, whereas in symmetric matrix we saw that eigenvalue of symmetric matrix is real, but also if it is positive, then it will be positive semi-definite matrix. Okay, converse, if since A is symmetric, you can write this like this. Okay, orthonormal basis of R power n. So if you assume this as a positive, to prove A is a positive, so you can just check with the proof. You can write like this. Okay, You can either start with this or you can prove with this. Okay. Now the second thing is also, if A belongs to R M cross N such that the columns of A are linearly independent, then A transpose A is invertible to prove A transpose A is positive definite. Okay. So if you have columns of A such as, so what will the case of this one? This can be tall matrix. So you can have tall matrix such that you all have the columns of A are linearly independent, then A transpose A is always positive semi-definite matrix. So you have to prove it. You can again use a simple theorem, X transpose A X. And you can write like this, and you finally you're getting as a norm of AX. And you know the norm of any vector matrix is always greater than 0. And anyway, if even A is a matrix, but the multiplication of AX will give you vector. So norm is always talk about in terms of vector, but even if the norm is talk about for the matrix, then it will be Frobenius norm. Means if the norm is talk about the matrix, then what the meaning of norm? Suppose A you have uh, x1 as one column, x2 as two column, then xn as three column, n column. So we can write like this. I'm just revising. So x1, x2, x1, x1, 2, x1, n. Okay. And this x2, 1, x2, 2, 2, 1, suppose. Okay. So any value I'm talking about, 2, 2, 2, n. Okay. So this is the columns. Okay. First column, second column. Now, if you write any vector, let's say y, you write x1 vector, x2 vector till xn, then you can write like square plus norm of A, which is also called Frobenius norm, is defined as mod of x1 square, this is mod, plus mod of x2 square, so on. This is norm. Okay. So what we are trying to tell, it is actually the sum of square of all elements of A. Okay. So what I'm trying to tell, you're stacking every column uh, below the each column, then you are getting. So finally, in fact, while calculating the norm of any matrix, you are also converting the matrix into a vector. Then you are calculating. Similarly, the norm for is in that way, the norm is always defined for vector. Even if it is defined for matrix, then you have to convert the matrix in the form of stacking the columns of A. Then you are calculating the Frobenius norm. So, okay, so that was just a glimpse. So, yeah, so a matrix, what we talked about, this A transpose A is always positive, definite, okay? We are talking about definite. Positive semi means this greater than equal to. Again, this is semi-definite, okay? So, a matrix A belongs to is called R power n cross n is called positive semi-definite definite matrix. And this matrix should always be symmetric, okay? So, should be greater than equal to, okay? So if it belongs to this particular thing, and A transpose A is symmetric positive semi-definite matrix. So any matrix, if it is belonging to R M cross N, so A transpose A, any matrix is always PSD. Very important to note. But previously what we had, if it is linearly independent columns are there, then A transpose A, that you can calculate as a tall or square, wide will not come here because linearly independent will not have in case of that case. So this is always positive definite, okay? But in this case, for A transpose A is always, you can prove by yourself. Okay. So if it is considered, if A is symmetric positive definite matrix, this implies that all the diagonal entries of R is positive. Okay. Second, determinant of A is always greater than 0. Okay. So first of all, what we saw, the how the positive semi-definite come into the picture. First of all, if we have any symmetric matrix and their eigenvalue is greater than zero, then it is positive definite. And when it's greater than equal to zero, then it is positive semi-definite matrix. And the most important criteria to finding the positive semi-definite is X transpose AX is always greater than 0 for positive definite, and X transpose AX is always greater than equal to 0 for positive semi-definite. Next, if we have a tall matrix or any square matrix that is having linearly independent columns, then A transpose A is always positive definite. Second, if we have any matrix that is belonging to R power m cross n, but the X transpose A is always positive semi-definite matrix. Next, the diagonal entries of positive semi-definite matrix is always greater than 0, and the determinant is always greater than 0. That's fine. That is more than enough for positive semi-definite matrix. Then this is what why A transpose A has positive semi-definite. We can prove this. You know, this A transpose A is always symmetric. Okay, that is fine. We can prove this bit. I'll prove. So we can prove if we have A transpose A. So X transpose AX should be greater than or equal to 0 criteria. So we have to prove X transpose A should be greater than or equal to 0. Okay, so this is what if we take LHS. So LHS equals to X transpose. I used to write vector by denoting down scripts. So A transpose A, X transpose. So AX transpose AX. This is what? AX norm of square. This is always greater than or equal to 0. That's why A transpose A is always PST. Is it clear? In fact, AA transpose, if we check with AA transpose, so let's check this AA transpose. So if we check LHS equals to X transpose A transpose X, then X transpose A, and this is A transpose X, this X transpose A, you can write X transpose A is equals to, okay, so this is what? Whole transpose, okay? So you can write X transpose A, yeah, so what it is? It is X transpose A norm square. So A transpose is always also PST. You can check in the internet. But yeah, I remember A transpose is also PST. Do you have any doubt? Anyone? Then we will move to the questions. Yeah, A transpose is also always PST. So that's why uh, you remember what is this matrix called? A transpose and A transpose A. I think this one is gram or this one is what name is there? Uh, Mukodhapa. Do you remember
Hilbert matrix, if I remember correctly.
which one?
Hilbert.
P got
Hilbert.
Hill. Ah, okay, yeah, yeah. Hilbert matrix. Yes. So this is Hilbert matrix. So both matrices are PSD. Okay. So any doubt can be taken in the next class, that is fine. And if we go to the last part, so this is what optimization f belong from R power n to R, minimization of this thing, point of, I think, Hessian matrix or what, I don't know what's that. I think this will be continued in the next class, that is fine. Moving to the question part, let's solve the questions. I hope you all have some understanding of the week 8. Week 8 was one of the most important 8 lecture of the whole course. What is a trace of this matrix? Let us solve this question. How can we find? First of all, let's find the eigenvalues. That trace will be definitely sum of the all the eigenvalues. Yeah, Lakshmi.
I thought trace was the sum of the diagonal elements.
Yeah, trace
Yes,
is the
of course.
sum of the diagonal elements.
So it's just 10 plus 50 plus 90, right?
Okay. Some of the main diagrams is that, yeah, trace of the matrix we also we can also find using sum of the eigenvalues. That's what. Yeah, in this case it is simply the sum of the eigenvalues, diagonal elements. The entries in the matrix square is the trace of it. Okay, but you can also verify using eigenvalues calculation.
Yeah, because finding eigenvalues is a lengthy procedure,
Yeah,
right?
yeah, very true, very true. That is straightforward. Huh. That's straightforward. Okay, this is actually one of the very easy weeks then. Let x belongs to the square matrix be such that one of the eigenvalues is 0. Tell me what is the answer. Then when which of the following is true?
It
Determinant
has
0.
determinant 0
And
and yeah, both A and B. So
yes,
D.
singular matrix is also true, right? Because if we have mod of A is equals to 0, then it is called singular matrix because in that case we cannot calculate the inverse of the matrix. Okay, so answer will be D. Okay. Okay, let's calculate this. Let alpha 1, alpha 2 be eigenvalues of a given rotator matrix. State which of the following is true.
B, B.
Yeah, yeah, true, true. In that case, we saw no 0, minus 1, 1, 0. Sorry, 1, 0. This was a rotator matrix and we had the eigen values as plus I and minus I. So, B. Answer is B. Also, if you can solve using cos theta minus sin theta. But if you keep theta as pi by 2, this will be the simple thing. Pi by 2, then this is the actual uh, expression for rotator matrix in the 2 cross 2. And it will be giving you plus I minus I. Okay. Find the product of the eigenvalues of the matrix.
8. 2 fours.
Yeah, very true. So a product of the eigenvalues of matrix is nothing but
Can we just
determinant of A.
check the previous one once more? I mean,
Yeah, yeah,
product
yeah.
of the product of the eigenvalues should be same as the determinant of it, right?
The product of the eigenvalue should be same as.
Determinant. And here the determinant is compulsorily 1, cos square theta plus sin square theta.
Yes.
And hence
Last option
number
also.
number 4 is also true.
Oh, okay. Determinant is cos square theta plus sin square theta is equals to 1. Then you are telling I and minus I. So yeah, wait, one more thing. This particular matrix is giving you this answer. But I think this particular matrix will give you different eigenvalues, lambda 1 and lambda 2. In that case, alpha 1, alpha 2 might not equals to 1.
No, no, whatever they give, the product of the eigenvalues of
But in
any.
that case, can you tell me the eigenvalues of this matrix?
Oh, you have to calculate the complex eigenvalues, but the product has to be same as the determinant. That's the theorem. Sum is equal to trace and product equal to det.
Acha, acha,
That's the
this one
theorem.
you are telling. Okay, okay,
Yeah.
okay. So answer is, yeah, yeah, very true. This is the answer and this is the answer. Okay, so it is written wrong. Okay, whatever it will be, but it should be equals to the determinant. Fine, fine, fine. Agree with you. Okay. Ah. Is the following matrix is a positive definite matrix? Please try to find it. How will we find? With the basic method x transpose ax is equals to greater than or equal to greater.
Yes, it's positive definite
How did you
because
find it?
the determinant is greater than 0.
Very nice. So one of
I
the
think
ways,
I think that's not sufficient. Determinant greater than zero, and along with that, the principal submatrix, their determinant should also be greater than zero to be positive definite. Only determinant greater than zero is a necessary condition which is not sufficient. Positive
So what
definiteness
is the
requires
principal submatrix here? What is the principal submatrix here over here?
that's it's one cross one cross one, two cross two, three cross three, like that. It's a 2 by 2 matrix. So principal submatrix here is the top left one.
1.
That is positive. Yes. Make that negative and then check. You will see that it's not positive definite anymore.
Okay.
that's great
So
observation.
If
the 2
the
by 2
first element
matrix,
is -1, then
Then the determinant
so
will also be negative, right?
yes, yes, yes.
can there be a case where A11 is negative but still the determinant is positive?
It can be, but in that case, that will not be a positive definite matrix. It's a theorem that all the principal submatrices, their minor should be positive. That actually leads to all eigenvalues becoming
So
positive.
let's take one example where suppose minus 1, 2, 2, 6, minus 6. Okay, let's take this 5. Okay, so minus 6 plus 10 is equals to 4. Okay, so here determinant is actually greater than 0, but okay, taking this example, okay, here determinant is 0, greater than 0.
What is the
No,
determinant
here
here?
determinant is negative still,
Negative.
right? Because
Okay,
it's
okay, okay,
minus
okay,
10.
okay, okay, okay. Wait,
Make
wait.
one entry negative.
Okay, minus 6 plus 10. Here it is positive, right?
Yeah, yeah.
Yes, 20 yes.
So let's check this x transpose ax. Okay, so if we check this x1, x2, minus 1, 2, minus 5, 6, minus 1 cross 2, 2 cross 2, 1 cross 2. Okay, so minus x1, minus 5x2, 2x1 plus 6x2. Okay, this will be x1, x2. Solve this. This is minus x1 square. Please correct me if I'm going anywhere wrong. Plus 2x1, x2. Sorry, x1 square plus 6x2 square. Is this correct? Wait, what I'm doing? Minus x1 square plus x1, x2 plus 2 x1 square plus 6x2 square. Please check whether it is correct or not. So this is x1 square, okay, minus 5x1 x2 plus 6x2 square. I think it can be written in terms of a minus b whole square. Any interpretation? So you are talking about uh,
X1, the x1 square was negative. No, that's okay. Okay. X1 square minus 5x1 plus 6. is this expression always positive for every value of x1, x2? x1 square will be there, but x1, x2, take the discriminant.
The- By the way, if we go with the basic concept also, if determinant is positive, okay, this is my interpretation, determinant of any A is positive. This implies lambda 1, lambda 2 is greater than is positive. Okay, greater than 0. But it doesn't mean that lambda 1 always greater than 0 and lambda 2 always greater than 0. It doesn't mean. So you are correct only that it is not a necessary condition. Sorry, sufficient.
It's necessary but not sufficient.
Yeah, necessary but not sufficient. We also have to check lambda and lambda 2 both are positive or not. In this case, it is fine.
Precisely. No,
Hmm.
in this case, it will not also be fine. We just check and see it cannot be expressed as a perfect square.
We cannot write, you are telling me we cannot write in terms of this A minus B square. Can you check the calculation? I think calculation is correct only. Guru Swami is telling minus x1 plus x2 square plus 7x2 square. What is this? Minus 7x. But this we can see from here. But if we check x plus 2 square 7x2 square. Okay, you are telling this is coming like this. Guru Swami. So in this case, there can be less than x1 plus x2. So it can be negative. Overall thing can be negative. If he's telling in the chat box, we can write like this one. Okay. So if it can be negative in the sense that it can be 7x2 square can be less than x1 plus x2 square.
Okay, see, I can give you a concrete reference of a book.
Okay.
It's a book is by Professor Rajendra Bhatia, Positive Definite Matrices, right? Hindustan Book Agency. And categorically, it is stated
Dr.
that
Rajendra.
Bhatia, I think he is in ISI Delhi.
Okay.
Book is, yeah, Positive Definite Matrices. The book is Positive Definite Matrices. That's the name of the book. It's from HBA, Hindustan Book Agency.
Okay.
And there is a stated that a matrix is positive if and only if it is Hermitian. I mean, this is given in terms of complex. So we are doing in terms of real. So our case, it is symmetric, and all its principal minors are non-negative. And it is strictly positive if and only if all the principal minors are positive. It's a theorem,
Okay.
actually.
Okay. That's great. Okay. Can we move ahead? Let's solve this question. Solve, I'm coming in just 1 minute.
So, just to summarize, to check whether a given matrix is positive semi-definite, not only do we have to check whether the determinant is positive, but we also have to check whether the principal submatrices are positive. Is it so?
Yeah,
Or
principal
determinant of
submatrix, determinant
By
and the
multiplying
principal
yesterday.
submatrix.
Yes, yes. Yesterday, sir has told
I
by
wasn't there.
multiplying x1 or x2, we can solve on both sides.
By what? Sorry? By multiplying x1 or x? Can you
Any
please?
on both sides. Yes. A into x1
Huh.
equals to right hand side also. Both the term are and use x1 transpose x1 is equals to 1 and x1 transpose x2 equals to 0, and second term becomes 0 here. So a is equals to gamma x1.
So, okay, I'm back. So, what can be the answer of for 6? Let gamma belongs to R, beta belongs to R, let x1 belongs to R power cube, x2 belongs to R power cube. It is given that x1 transpose x1, x2 transpose x2 means all the norms. This one. Find the eigenvalues of the matrix. Anyone solve this question? So basically, x1, x2 are orthonormal to each other, and their since their magnitude is 1, and they're orthonormal. Okay, find the eigenvalues of the matrix. Anyone who solved this question? So yeah, actually this will give one matrix. This will also give one matrix. So if you go x1, x2, x1, x2, it will be 2 cross 1, 1 cross 2, 2 cross 2 is this. So x1 square plus x1, x2, so on, so. Any idea how to approach this problem?
Multiply both side by x1.
Okay, in the right side. Okay, then it will be 1 gamma
1.
x1 plus beta x2 transpose x1. This is also 1. Okay, nice. Now multiplying both side by this is tricky. Multiply by x1, x2 transpose x1, x2. No, it does not need to work. Let us take transpose. X transpose A transpose. No, it's
I
not
think,
going to work.
I think the first part is done. The x1 is perpendicular to x2, that vanishes. So you are left with ax1 equals to gamma x1.
Wait, can you repeat?
The first line you have written,
Yeah.
the right hand expression is 0 because x2 transpose x1 is 0.
Oh, okay. This one you are telling. Okay,
Yeah.
okay.
And then simply it is, yeah, that means gamma is an eigenvalue.
Okay, that's nice. So gamma,
Similarly, you multiply from right with x2, and then you will see that beta is an eigenvalue.
and how zero is coming then?
Is getting multiplied with x1 transpose, x1 transpose x2 in the first expression,
Okay. X1
right?
transpose x2.
Yeah, that is 0
Actually, it is giving you zero.
because that is given.
Okay,
That's one of
okay.
the given condition.
Okay. Okay. So if you multiply it by x1, you will get as gamma. You multiply by x2, you'll get beta. And this condition is showing that lambda is equal to zero. So answer should be B. Okay.
Just a minute. How do you conclude the third lambda equal to 0 from these two?
No, first one only. This.
This means these two eigenvectors are orthogonal. It's a 3 by 3 matrix.
So determinant, okay. So determinant of A is actually 0, then it is
Yeah,
telling,
yeah. Determinant is 0. That's it.
yeah. Determinant is 0, then it is telling that one of the, this is 0. Okay, if you multiply this one, then you'll get this. Multiply x2, you'll get this. And finally, if you take this, determinant of this one is 0. Thus, determinant of A is 0. Okay, x1 transpose. If you calculate this determinant is always 0. It's telling this. And then, because it is a sum of this particular thing, alpha and beta, then it is showing determinant is also 0. That's nice. Okay. What will the eigenvalue of this particular thing? AQ. That is from the property of eigenvalue, eigenvector, we can tell. It will follow lambda q minus 4 lambda square plus 2 lambda. So we have to check one of the values which is following this.
Option A
Okay. But for which lambda value you are getting?
for 4.
4. Okay. For 4, if you put it here, you'll get 8. That's fine. Here it is given in terms of uh what was that theorem? Singular value decomposition. But we will talk later. Okay. The value of alpha should be, you can directly determine the determinant should be greater than 0, and trace is lambda 1 plus lambda 2. And you want A to be positive. For both eigenvalues of A to be positive, the value of alpha should be. So calculate this. 9 alpha minus 7 is lambda 1, lambda 2. And lambda plus lambda 2 is equals to 9 plus alpha. And we have to solve these two equations. If you keep lambda 2 as 9 alpha minus 7 by lambda 1, and you put it here, and keep the condition as lambda 1 should be greater than 0, lambda 2 should be greater than 0, then it should give. Or here it is written, for square matrix, the determinant of the positive eigenvalues. Hence, for the eigenvalues to be positive, okay, these two values should be, so directly you can keep this uh, lambda 1, lambda 2, the determinant should be greater than 0. So alpha should be greater than 9 by 7 by alpha 9. So see how I approached the problem. I approached through by solving these two equations. But one can see directly that if the determinant is positive, then for the eigenvalues will be also be positive. So directly it can be from this equation. Okay. So yeah, so this is very straightforward. If A is a 3 cross 3 be a real symmetric matrix, then the eigenvalues of A always are real. It will be real. So yeah, Guruswami, we did not say that a determinant of x trans. Yeah, why? Because see, the A is written in terms of these things, right? A is written in terms of gamma x1 transpose plus beta x2 transpose. So you are telling if determinant of x1 transpose is equals to determinant of x2 transpose is equals to 0, then you are telling determinant of A will also be 0, because it is anyway that multiplication is there. And a determinant will be always uh, it can be written directly the sum gamma x1 transpose plus beta x2 transpose. That's why I think rank A is less than 3 is easier to see here. Oh, that you can also see. If it is less than rank is less, then definitely one of the eigenvalue will be 0. 3D, how it is easier to see?
The right hand side are rank 1 matrices, both are rank 1.
Okay.
So, two rank 1 matrices, their sum cannot be rank
But
3.
no, it is not rank 1. How it is rank 1? X1?
X1 transpose is rank 1 always
Wait,
because
wait.
it's
If you write this X1 as belongs to
right. It's a
X
column,
column.
and
Okay,
X
okay, okay,
transpose
okay.
is a
Yes,
row.
yes,
So
yes, yes.
multiplication every column is a multiple of X1.
1 cross 1. Okay. That you can also see. That's great observation, guys. Okay. Okay, that we know. Last question. Yeah, that again you have to solve the eigenvalues. Uh, trace and determinant. You can solve using two equations. Can anyone tell me? This answer is A. Okay. Again, we have to solve these two equations and we will get directly. So I think the questions of week 8 here are easy only. Only this question was little tricky, but yeah, even if we try to observe properly, then we can see this question also.
Yeah,
And
this year, this present time week 8 assignment has one question which is completely different from this genre, which is of cosine of a matrix.
okay,
That
cosine.
I requested yesterday the other gentleman who was teaching us that if you can give some material where we can read this kind of
Okay.
things.
Okay, first of all, I'll go through the current week 8 assignment. Then I will see like
Yeah,
cosine. Can you tell me the question number
yeah,
also?
yeah. The question number I'm telling you, just give me a second.
Yeah.
The question number is question number 9.
Okay. 9. Okay. Fine. I'll go through it. Then we will solve the
Yeah.
question.
I don't require solution of this particular one. I want to read similar things from some literature. So if you can refer some literature,
That's true.
uh,
Yeah,
yeah,
yeah, yeah. Anyway, the main intention should be learning. That's fine.
yeah,
Yeah.
yeah, yeah.
Okay. So thank you so much for joining. So if you
Thank you
have
very
it,
much.
yeah, if you have any other doubt, you can stay. Otherwise, you can leave the call. Anyway, we have covered the week 8, and sometimes I am also learning with you. Like I just watch the lectures with 2x, and then I solve the problems because I have already some sort of knowledge in this linear algebra and all. But yeah, how to approach a problem is also very important in these aspects. How you see, how you perceive it, how your pen is starting. The first thing is this one only, because if you don't start well, then you will get indulged in that thing only. And try to remember the concepts, that this is the thing, that is the thing, that the basic thing. And other thing is that you can directly derive. You don't need to remember. Okay.
Can I ask one question about assignment 7?
Uh,
Just one technical question, not some specific thing.
okay, okay. Yeah,
The
please.
idea is those questions of assignment 7 this year were all computer
Programming.
based things. Yeah, programming based things. So I'm
Yeah.
not at all conversant with that. So my question may be very naive, but since I'm trying to learn it, it will be very helpful if you can give some answer. The idea is uh, like the very first question,
Yeah.
we have to generate certain data by
Yes.
computer.
Huh.
So even if we maintain the required condition, every time I generate the data arbitrarily, random generator,
Huh.
there should be a different set of data. So with
Yes, yes.
respect to that different set of data, if I approach a certain problem where all the other parameters are fixed with respect to that generated data only, is it the case that the answer to the problem is uniquely fixed? It doesn't depend on the generated data. I mean, apparently the question, the way they are set, there are only four specific options, and at your end, you know one of the answer is going to be correct. So
Yeah, yeah.
does it mean that this answer is bound to be correct, irrespective of whatever the generator, the data generator may generate? I mean, theoretically, independent of the generated data,
It
can this
should be
answer be
unique.
stated? That means the data as such has nothing to do with it. I mean, whatever data the practical problem may have within that particular limit, the answer should be unique. Can that be proved theoretically?
Oh, okay. It can be proved.
I
Yeah.
mean, yeah, that would have been very nice to know because you see, I hope I could clear my. Actually, I could correctly pose my question. My confusion lies exactly here that if I tend to generate it again and again and again by my machine, every time supposedly I am going to get different set of data, and then I run the same program on it. If the
Yes.
answer D is correct, does it mean whatever data the machine may generate, the answer will always be the last function? Does it? Yeah,
Yes.
it will depend on the
So,
data.
so answer is it should be unique only, irrespective of the what data you are generating, and proving it theoretically. We
Because
need to.
then
Uh,
practically the data then practically the data becomes sort of redundant, that if there is a problem of this kind, we know that the last function is going to be the answer. Is
yeah.
that true?
No, no. A redundant won't like affect here. The concept will be okay. Question number 7. I'm noting it.
And it's question number 1 of assignment 7. Say for example, all the questions are very similar in nature,
Okay.
because apparently we are asked to generate certain data from some data set, but that generation is supposedly random. The machine is generating it. So the answer at your end, from the pattern of the question, it appears that the answer is unique. You already know it, that what is going to be correct answer. So it doesn't depend at all on what data we are getting at our end by the machine. That means
Okay.
these questions have unique answer, irrespective of data. Am I getting something wrong? Am I missing something?
No, no, no. You are correct in your own way. Like you are, yeah. It should not depend on the date.